So our next presentation is by Nitesh Turaga, who is also a member of the Bioconductor core team. And today, Nitesh will be presenting about the efficient use of Bioconductor in a cloud computing environment. So Nitesh, if you're able to share your screen there, just make sure everything's working.
Can you see my screen?
Yep, that's fine.
Hit present.
Yep, that's the right screen there. So
okay,
I'll pass it over to you.
Thank you. Hello, everyone. My name is Nitesh Turaga. Thank you, Pete, and the organizers of BioC Asia for inviting me. I'm a scientist at the Department of Data Science in Dana Farber Cancer Institute, and I'm also part of the Bioconductor core team. And today I'll be talking about the efficient use of Bioconductor in the cloud. So before we get started, I'd like to share the link to my slides. It's bit.ly bioc-cloud-bioc Asia 2021. And there's a picture of a beach, hopefully to get you all in the right spirit. So without further ado, let's get into it. So as Lori touched on a little bit, Bioconductor is primarily being used on local machines where users have to configure and everything by themselves, right? Like, so they have to install R, they have to install Bioconductor, they have to install all the system dependencies needed for R, like Java, Fortran, GCC, and so on that local machine. And then once all of that is done, if they want to use certain packages on Bioconductor, they have to install, which essentially means compiling those packages on the base operating system which they're using. So on the right-hand side over here, you'll see a typical package installation process. So someone says BioC Manager install, which is the traditional way to install a Bioconductor package. And it'll complain if you have any missing package dependencies, which are not in the description file. And then you'll figure out what system dependencies that needs. And then you'll try to install those missing packages with BioC Manager install. And essentially you repeat this process till you succeed in installing everything you need to get your analysis going. So there are two problems here. One is the configuration of the local machine. And the second is the compilation of the packages, which takes a bunch of time. We're able to use certain systems built for the cloud to make these two problems work for us and make them more efficient. So how do we do this? And this is where containers come to the rescue. Containers are essentially building blocks to create end-to-end solutions for cloud platforms. They are lightweight virtual machines, and Bioconductor produces containers or Docker images. And you don't have to worry about what Docker is. Docker is just a type of container engine. If you want to simplify it a little more, it's just a piece of software you need to install on your machine. These Docker images are very easily downloadable on your local machine. They're hosted on open platforms and they're publicly available. We named them in a very simple way so people can remember what they're called. They're called Bioconductor_Docker images. So this is the name of the image, and the Bioconductor you see in front of that is the name of the organization inside the registry. Docker Hub is the most popular registry for hosting Docker images, and Bioconductor has an account there where we freely distribute these images. And the Microsoft Genomics team produces an official mirror of the Bioconductor Docker images on the Microsoft Container Registry. And this is also freely available to everyone. So you guys must have heard by now, since you're at the Bioconductor conference, that the Bioconductor latest release is out. It's 3.14. And as of a couple of days ago, the latest Bioconductor Docker image is also available. So if you try to pull the Docker image with the tag release_3_14, you should have that available to you now. So we described two problems. One is configuration, the other is compilation. So let's see how these Docker images solve these problems for us. So these Docker images are lightweight virtual machines, and they come with a bunch of system dependencies installed in them already. So when you download a Docker image, it comes with system dependencies. And why do we install these system dependencies? Is so that you can install almost all of the Bioconductor packages without any problems. So we make sure before we ship the image that it installs over 99% of the Bioconductor packages. So just to put that into a little more context, there are 2,083 software packages, I believe, in this release, if my memory serves me right. And the latest Docker image is able to install over 2,050 of them successfully. There are certain packages which won't install because of the way Docker works. And there are certain packages which we don't want to install because they increase the size of the Docker image beyond what we are willing to ship. There's also other added advantages of these Docker images. It comes with an RStudio IDE. So if you're someone who's used to using RStudio to do all of your R work, you get RStudio for free. It's also cross-platform. So if you want to use, if you're using a Windows machine, you can use these Docker images. If you're using a Mac, you can use these Docker images, and the same with Linux as well. So the other advantage to these Docker images is just like you're able to use these images on your local machine, you're also able to use them on cloud virtual machine instances on whichever cloud you have access to. And you're able to skip the configuration part of these complex packages and system dependencies easily. I want to say a word about how popular these Docker images have become in the recent past. So we have a little package called BioC Docker Manager, and there's a function called available within this package. It spits out a tibble, and it gives you the list of images which Bioconductor produces. And the first one in the list is Bioconductor Docker. It's sorted by the number of downloads. And you can see that Bioconductor Docker has over 200,000 downloads from unique IP addresses. So if you download from the same computer on the same IP address, it doesn't register. So this is over, I think, 4 releases. So it's gained a lot of popularity in a very short period of time. All right, now coming to the second problem, which I spoke about, which is compiling these packages on the local machines. So we can solve this with something called binary package installation, and we provide a package for that. Lori touched on this briefly. It works only with the Docker images we produce or any of the Docker images which build on top of the Bioconductor Docker images. It's a very simple function. It's called Anvil install. The package name is Anvil. The function name is install. And it takes a list of packages, a character vector of packages, just like BioC Manager install. And the reason it's so fast is because there's no compilation involved for any of the packages which you try and install from Bioconductor. So let's describe this process a little bit more, like how exactly does this work? So you say Anvil install, and you give it one package, or you give it like a character vector of packages. What happens is it downloads that binary package from the cloud. And then all it does is it points your library search path to wherever it got downloaded to. That's it. it doesn't actually compile anything on that local machine or on that hardware. These images, these packages are always built for the specific Docker image and the configuration of that Docker image. So it's important to realize that these packages don't work on your local machine. But if you install Docker, use the Docker image, you will get access to these binaries easily. So I keep saying it's really fast, but I have to prove it. We're all scientists here, so we have to prove something we say. We're going to do some benchmarking. I'm going to use a package called micro benchmark, and we're going to test two functions. The function in the orange is anvil install, which does a binary installation of the package. And the second function, which is BioC manager install in the blue, does the traditional installation. And we're going to try and install two packages, rhtf5 and rhtslib. And we're going to try and install it 20 times. With benchmarking, you repeat the same experiment multiple times, so you get an average of the results. We're going to save it into an object called res. And I ran this ahead of time, obviously, and I copied the results here. It'll take a bunch of time, so we don't want to do that live in a demo. So if you print out the results, the units are in seconds, you'll see that the binary installation took about 7 seconds for the two packages, and the traditional installation took about 71 seconds. And each of these functions was evaluated 20 times. So that's almost a 10x speed up. And you'll see even more drastic results if you take one-off cases where you see the max time is almost like 114 seconds. So this goes to prove that binary package installation is very quick. There's two ways you can launch these Docker images and take advantage of both of these features. So you can either do it on your local machine, and you can also do it on the cloud, where you can launch stuff on Azure container instances or the Google Container Engine. And if you do use these Docker images on the cloud, the download speeds of the binaries you get are much faster because there's not as much egress from the cloud to a local machine. It's all locally provided within the cloud. And if you want specific instructions on how to launch these Docker images on Azure, like the Microsoft Genomics team provided very helpful documentation on the website, which is linked here, and you'll be able to set yourself up very easily. Let's talk a little bit about the adoption of these Docker images. I already mentioned that it was really popular, but I just want to mention a few of the organizations that have used it. So Melbourne Bioinformatics has the Genomics Virtual Lab, which uses these images. The Galaxy platform, which is very popular in the bioinformatics community, uses these images. The Renku platform in Switzerland, hosted by the Swiss Data Science Center, also uses these images. And Anvil, more recently, which is a consortium formed in the US, I'll talk a little bit more about the Anvil later on in my talk, also uses these images. All of them have used the Bioconductor Docker image as a base image and built on top of it a little bit, so it fits their system requirements. So what are advantages of the cloud? Why do you need to use these Docker images on the cloud? I'd like to take this opportunity to present a table. It compares 4 concepts: whether you need to configure the machine, whether you need to compile the packages, speed of that machine, and scalability. I'm trying to demonstrate here that using the cloud and a Docker image provided by Bioconductor is the way to go for being the most efficient you can be. So on the cloud, you do not need to configure your machine. You just use the Docker image as given. You do not need to compile packages because you can use binary packages, which we provide. Your speed is based on the compute size of the virtual machine you launch. And you can scale the size of your machine up and down as required for your needs based on the time. So it encapsulates both the scalability and elasticity of the cloud, whereas the other two systems do not. So if you use Docker on your local machine, it's limited by the memory and the hard disk space you have on your local machine. And it's not really scalable because, again, it's limited by your local machine. And if you just use your local machine, you have to configure your machine, you have to compile your packages. You're limited by the size of your machine in terms of speed and scalability. So definitely the clear winner I'm trying to portray here is using these Docker images on the cloud. So there's even more cloud solutions available. So say you're one of those people who does not want to learn Docker images or anything about Docker, and you just have a credit card and you're willing to plug and play. There's a new organization called the Anvil Project. It stands for Analysis, Visualization, and Informatics Lab Space, which Bioconductor is part of. And we help build this solution on the Google Cloud. It's coming to Azure really soon. So it's available on anvil.terra.bio. You're able to make an account and use it very easily. I recorded a demo for this. Hopefully it plays. The reason I recorded it is because this is a live demo and I don't want it to go wrong in the middle. So I'll just play it really quick. So in this demo, I'm going to sign in with my Google account. It seems I've already signed in. And there's these ideas of workspaces. You can create a workspace to do all of your experiments in that workspace. I've already created a workspace called Nitesh Test Workspace. I'm going to search for it, launch it. And then we have something called cloud environments. So I'll pause here really quick. And in this cloud environment option, you'll see that you have applications, number of CPUs you want, how much memory you want for each system. And then I'll choose RStudio. Here it's running Bioconductor 3.13 because it hasn't been updated to 3.14 just yet. It'll happen in this week. And this system is using the Bioconductor Docker images, which we provide. And I hit create. This is going to take a couple of minutes, but I fast forwarded that bit so that it's easier to watch. And then if I hit this little R icon up top, it'll open RStudio for me. So we have RStudio right now. It's running R version 4.1.1. And I'll do a quick check with BIOC Manager valid to see if everything is okay on this RStudio instance. And this will tell me that there's a few packages out of date. I could say yes and install them, but I'll say no for the sake of time. And then I want to demonstrate a binary package installation with this package Anvil install. And I'll install this package BIOC parallel. And you'll see here that it finishes really quickly. So BIOC parallel actually takes a bunch of time, but here it really doesn't. It's essentially a matter of seconds. I did not speed this up. But if you look at the output of this, it'll just say installing binary package snow, which is a dependency of BIOC parallel. And it'll also say installing binary package BIOC parallel. Both are done very quickly. And you can see the download links here, which says storage.googleapis.com, which is essentially a Google storage bucket, which is hosted by Bioconductor. And we store these binary packages on that system over there. So Anne will install points to that location, downloads the packages, and your R session knows that these packages are now available. And that is it for that demo. So I'll pause that, exit out of it, go back to my presentation. And that's it for how to use Bioconductor more efficiently on the cloud. I want to say thanks to the Bioconductor core team, Marcel, Lori, Jennifer, Irvin, Kayla, Vince, Martin, and Rafa, who've been very supportive. And if you have any questions, feel free to email me or ask me right now. This is my email address. Thank you very much. I do not see Pete. There we go.
Thank you very much, Nitesh. So we've got questions on Slack, and I'll just read a couple of them out
Okay.
in the time we have remaining. So one of the questions from Kozo is whether we will be able to use Azure, or I'm not sure how you pronounce that, Azure credits for Anvil for Bioconductor. He says that at the moment he thinks he can only use Google Compute Engine credits.
When we'll be able to use?
When or if, I guess.
I don't know how far the Azure development has gotten on the Anvil, but I'm thinking early next year, I believe. But if you want to use Bioconductor on Azure, like I think the best way to do it right now is to go to that link in my slides where you can launch the Docker image on Azure and use a compute instance on your own.
Thank you. We had a question from Stephen Peterson saying, first of all, thank you, it's a really helpful talk, and asked, is there a list of Docker compatible packages or a badge on the package page to indicate which packages are available?
So we didn't do that mostly because it installs almost all the packages. Like, I mean, it would just be like every package is compatible except XPS and like a few random ones, which are almost like impossible to decipher. So no, we don't have a badge right now. So the best way to do it is just try and install it and it'll work 99.9% of the times. Yeah.
Wonderful. And a question that sort of came to both you and Laurie, and I might kind of merge this in with my question, was that how do the Anvil binary packages compare or relate to some efforts from like OpenSci and RStudio Package Manager for supplying binary packages?
Exactly. So RStudio Package Manager, as far as I know, don't provide Bioconductor package binaries. They provide CRAN package binaries, which the Docker image uses, by the way. So if you wanted to do like a binary package installation, or even with just BIOC Manager install, it should take CRAN packages from the RStudio Package Manager. So you'll get both the binaries from Bioconductor and CRAN. So we're using that system and our own system to provide binaries for Bioconductor.
And is there
they don't provide Bioconductor binaries, as far as I know. Yeah.
Okay. And is there any comparison to what our OpenSci are doing with their, I think it's called our Universe?
I don't know enough about that to answer that question, but I can circle back on it.
Yep, that would be good. So thank you very much, Nitesh. There will be, yes, if you have a look on the Slack channel, you might find a couple of other questions, but we'll take a couple-minute break. And at 2 p.m. UTC, 4 p.m. Melbourne time, basically in 3 minutes time, we'll start our next talk with Yunshin Chen. So please join us again then.
Thank you, guys.
Thank you, Nitesh. Thank you for staying up.
Yeah, no worries. See you. Bye. Good night.